Today I will talk about kernel exploitation, about some buffer overflows, and introduce some new technique. It will be kind of complicated, so we go through some checkpoints. We turn some stack overflow to buffer overflow. We introduce some new post-paying technique, and so we deal some sloop and other things. And we will take it by example, which we discovered last year. Those be some are modified Trinity fuzzer. We modified Trinity fuzzer for Android, and we discovered this in current joint phones, which because this bug is about splice vulnerability, known from 2012, but it's applicable for most of the phones and the current market. And triggering this vulnerability was quite simple, just two threads, one of the resizing the size of the pipe buffers, and the other one just calls to splice functions, is called. And it was back at pipe buffers, which is basically the index, the counter of the buffers. And that means it was out of lock access in setting the size and in this splice the pipe. And what's happened, it was that when you have these pipe buffers at low index, it will do fast malloc. So it basically use the buffers located in the stack. And when it's the big value, it will k-malloc the buffers from the pool. And in this case, which was the panic lock, it was that it was racing to increase the buffer counter, and it was used before was used buffers from the stack, but at the end it was checked this value again, and if it's big, it will k-free that blocks, memory blocks, but it's on the stack, and free on the stack means panic. But it was not only the case of this particular function and the Vim splice, but it was also introduced it present on many other functions. And we choose under candidate. It was default file splice rate, and it was really perfect because it have free buffers, free members on the stack which can be used. And in one of the members, you can override it with pointer and with page size. And this pointer points to your data, which can be controlled. And it can cause the stack overflow. And that's really nice. That's one limitation is that we overflow with some pattern the kernel pointer to our data and the size. The second was on the issue that in Android, you have plenty ROMs. That means that you implement some, let's say, exploit for one ROM, and which is the stack looks totally different, like in another ROM, because it depends on how it's compiled, about some defines, etc. So you have to when you go by attacking the stack. In this case, it's possible because there's no canaries included in Linux kernel in Android in this function. And in this case, you can target the return pointer, or you can target the params or local variables. But every time when you target different ROMs, you have to specify, because the stack will look different. And doing this stack pwn is possible because panic was about k-free on the stack, and it's most likely happened most of the times. But you have one option: the raise two times. The first time to increase it and overflow the stack, and second time, before it will be finally k-freed, we will decrease it again. But in this case, you have a very low possibility to do it, because you have a really small window for racing two times. That's the first thing. And second thing is that even if you do it, you need to handle with all the forms. So that can be a problem, and it will be not reliable enough. So what's next? But next can be buffer overflow. You can overflow to pool, not to stack. And tactic will be that you will, at the beginning, it will be this pipe buffers really big, so it will be not allocate the phase alloc from the stack, but it will be 2k malloc from it will be 2k malloc, and it will be raised to be even bigger, so it will overflow at the pool. And so at the end, when it will be k-free, everything is fine. You just overflow at the pool, and it can survive. But the other problem is that you overflow not only with one structure, not only with some kernel pointer and size, but you have also two other members, which is overflowing same time. So that means that you overflow not only with from one slab, but you overflow in 3 different places at the same time. So it can be a really big problem when you want to build some stable exploitation or some routing. So we need to handle this one. And the other thing that I mentioned before, that in this case you not overflow with totally arbitrary data. You overflow with kernel pointer and with the page size. And the kernel pointer is this feature. I have one feature that it points to your data which you can control. But on the other side, we can avoid to overflowing from 3 places, and we can overflow just from 2. But for this, we need to exit sooner. That means that it will fail by reading to our kernel pointer, to some memory which points this kernel pointer to. So this is a side effect. That means that on this memory, which points this kernel pointer to, it's not control data anymore. But on the other side, it's big plus is that you overflow just only with two buffers in 2 places at one time, not at the 3 places. So it can escalate your exploitation rate. But that means you are not able to control that anymore. Only if you don't use pool spray. But pool spraying can be kind of hard, especially when you have a 60-bit platform. But for that, we introduce some new pool spraying technique. We use also this default file splice rate function, because you have the alloc page, which will basically allocate for a new page, and the kernel reads, which reads the data to the page. But it has on the other side some problem, because you can allocate, you can create only about 212 pipes in one process. So it can be a problem, but on the side, when you have kernel underspace randomization, not kernel space randomization, but when your allocator gives you by kmalloc some randomized memory, basically it's good enough, because when you have, for example, 100 pipes, and every time you try to allocate some memory, it will allocate something down the place. So you will repeat this many times, and you will cover a lot of address space, and you basically fill all the address space with your pattern. So, but it's kind of complicated to do this pool spray in this way, because you need to use pipe and ship data to this pipe with splice, and take at the same time the default file splice rate function. But for example, for sockets, for pipe, it took under function. But for TTI, it uses exactly this function that we need. And for this, we just use pipe, splicing to write to TTI, the splice to pipe, and we got it. And we repeat it many times. We write for a few seconds, and we get sprites memory. And it's really lightweight, because you just use about, let's say, 512 pipes, and it's no big memory pressure, but you fill all kernel with your pattern. And when it comes to implementing this kind of, let's say, not easy stuff, let's say it has a lot of steps that you need to fulfill. You need to implement some mechanism, some clean way that you on the project you will reuse it. So that's why it doesn't matter. And at the end, you just end with this one. That's you just provide the buffer and size the buffer, and we will spray through the memory. And let's say wait for some time frame to be the memory space successfully sprayed with your content. And at the same time, why it doesn't matter is because when you implement this kind of vulnerability, like for example, this splice, it also needs a lot of steps. Because up to buffer overflow, you need also fulfill a few steps. And after buffer overflow, you need to fulfill some other steps. And it's kind of complicated process because it's a really different exploitation these days, like it was, for example, before 10 years. Now it's make some proof of concept for exploitation. It's really kind of coming to be a difficult task, and you need some engineering put inside. And it's more be like a developer, less be than the hacker. And on the side, as I said, that okay, now we can spray our data, we can overflow. But the problem is that still we need to overflow to something that we already control. And for this can have some words, for example, some randomization when it comes to kmalloc, return the chunks. And also that, but it's some limitation because when you get some chunk from the kmalloc, it will just return from some current slab. And so these slabs are organized by size, and every time it's basically can be reused, this slab, chunks from the slab. So what's the plan? Plan is that you allocate many memory objects the same size. So that means you create a lot of slabs. So you will create and empty a lot of slabs. And what you do next? That you will free on that red points. That you will free some of the objects, and then try to allocate your buffer on the object which can be overflowed from. And later on, you will try to trigger the overflow and POM. It can be also, it's not so stable, and it can be some experimenting, but basically this idea which works. It's not 100%, but it works quite stable. What can be complication? In the splice case, it was not too much, it was not this case, but in a lot of other exploits and other vulnerabilities can be this case that memory object separation. That means that, for example, in Linux, you have caches. And in Linux, cache is sometimes, many times used for different objects, have some different caches. And that means that in this cache is only this object or some few other objects, but you can manipulate with that objects. So it can be a problem that when you allocate, okay, from this cache, from this lab, you allocate a lot of chunks, but you can overflow only to this, but you cannot control it. But for this is also can solve it, basically because the cache is also just chunk of memory, and when it's full, it have to be allocated new one, and that can be your point, that you allocate new kernel cache for this object, and you position it right after that buffer from you can overflow. So basically, you will overflow to that cache. It can be like in this way, but it's really more complicated. And on Windows kernel, it's a bit easier because it have, let's say, just sessions. And in every session, it's a lot of objects. And in this object, and a lot of objects which from user mode you can allocate or free and somehow would control the content. I call them really powerful objects. And so in Windows kernel, it's no big deal with like from the kernel caches. And so why is this possible? Because I think in a really secure-oriented operating system, buffer overflows should be mitigated by design. At least the buffer overflows like we know it nowadays. Because the main pinpoint of this operating system is that you can have from user mode directly the control allocate or free memory object in kernel. The other thing is that you can control the content, or you can control at fully the content, that you can have the same data, like in user mode, except some header. Or you can predict that, okay, there will be some plain pointers or some members which know that the size will be not higher than this one. So you can somehow semi-control that object. And the really big fail is when this object contains also some plain pointers on the functions or on the buffers, which can be later converted to on the vulnerability and can be misused. And also, these kernels, operating systems kernels are going to be object-oriented is okay, because I think it's the right way to go, because we need a lot of modularity introduced into the kernel. But for this, you need to also do some integrity checks, because when you once alter the objects, you can point all the kernel, and that's a big deal. Another thing is that we have 64-bit 64-bit address space, and it's introduced a lot of new opportunities. And basically, when it will be some early secure-oriented operating system, that every chunk can be like it's basically it's a page heap, I think. That you have before and after, you have some sentinels you touch with overflow and it will kill you. And in 60-bit platform, it can, okay, maybe it's not will be very efficient, but it can be somehow played and can be going to this direction. So what was covered by Espresso about this vulnerability? It was that what it means for the splice. It was that introducing that triggering the bug was not so hard, because racing was very primitive. But what was not primitive was that you overflow at least from 2 buffers at the same time. So it means that it's not stable too much, because you can pawn some buffer, but meanwhile you corrupt some on the memory in some kernel. So to successfully pawn it in higher level, you have to really fix these issues, and you have to have some luck. So it's at the end it was about, I think, 1/2 of 3 from 4 point success. And we also showed some new way how to spray data to kernel memory. It's fast and effective, and some ideas how to play with swap. But when you want to play more with this vulnerability, you need to do some more research about what is your target. Because, as I said, in this vulnerability, you overflow with some kernel pointer at patch sites. It is the pattern which is repeating, and you need to find your target. Because, for example, for last year was some TTI vulnerability in TTI buffers, and it was used some good technique that it was overflown to TTI buffer structure, and it's introduced a lot of some function pointers. But on the other side, it includes also some magic. And when you override this magic, it will panic. In this case, you cannot override this magic because you override just with kernel pointer and page size, and it's the problem. And the other things that you need when, for example, with 64-bit devices, it's going to be enabled also the access mode prevention and execution mode prevention at the user mode data. So it's very good to also play with these things. And I said that it's one hint was that for TTI it was a TTI buffer, but we need to introduce some other thing. The one thing was for this, when you trying to, you can control the buffer, but to just some limited scope, because you can overflow to not to every size, but only to some specified sizes, which is 16, 32, and etc. But it's multiplied by size of pointer. So you end up with some limited slabs which you can use. And for this, you need to find your target. And last time, in current date, it's going some problems with some software security and research. And I want to react a little bit on this one, because usually attack chain and vector is that, for example, because you have antivirus and it protects you and the companies from getting compromised. But the attack chain is that at first time you need to get somehow into attacker's computer. And for that you need some social engineering or some vulnerability. And for example, we focus on vulnerabilities. And when you got vulnerability, it's the other thing that now is proactive solution, that it's somehow how to prevent to install computer is that you limit the vulnerabilities to 0 days, that you kill the 0 days, and that means that it will not, it will be far more expensive to do research and to attack some targets, because one time when this prevention when it's basically a pawn system, it's game over for it's a game over for especially for the companies. For user maybe not, but for companies it's game over. So I think the proactive protection is really necessary. And for this, basically we are popping calculators, because with popping calculators you killing all the low-hanging fruits, you grab it, and what's the rest? It's really hard to find. And we are going to this direction, but it's really need to understand this methodology. And for this, I see on the Twitter that supports security research, because it's really important. It protects especially the companies. And also, in a lot of conferences and all the guys asking me basically what we are doing. And we are based in China, and we are security researchers. And basically and we do a lot of stuff. And this kind of our history, that's at the beginning, we are core members are the people from with the very good security base and the good code of ethics. A lot of guys working for Microsoft before, and also I was working before for antivirus company, and so the other guys was working in China for some other security companies. We also was, and some other guys was working with Zero Day initiative to cover all the bugs. And we also attend a lot of events like a Pontoon, 3 consecutive years. And also we get some awards from Zero Day initiative or from Tesla, and we also make some Geekpwn events, which is something like Pontoon but for devices. And we also support the young guys with CTF games, etc. For example, we have some interns with Zero CTF or Blue Lotus. Zero CTF won the Code Gates, and Zerops win the Code Gate, and also Zerops and Blue Lotus qualified for this year DEF CON. And also we do something for the geeks. Last year we also get some new vulnerability in Linux, and we report it. And every time when we got some vulnerability, we report it to be fixed. And as this time, we report it, and also afterwards we make some tool for geeks that can root the Galaxy S6 phones. And the other thing is that we introduce new techniques and try to share with people. I make some highlights. For example, we make some WebKit exploitation techniques. In Syscam, we also make some how to play with page tables and pawn with WAD roots. And also we introduce in public the CCC shellcoding framework for the people. And also this time at Recon will be present some technique how to by one bit flip, basically by right where you can pawn all the kernel, including the kernel code execution. And also our team trying to share knowledge worldwide. This is just some highlights, but I also don't mention that out of dozens of China domestic conferences or lectures and universities. So we're trying to share and spread the knowledge. Now the thing that I said that our team creating the Geekpwn event, which is basically the event when you can choose your own device and try to pawn it. Just send your proposal to us, and when you think that it's really good, you can go for it, and maybe you can win. It's in some magic date about 24 October, and this will be second year. So you're welcome. And basically that's all. But we are hiring at the same for that we want also some interns. And ask the questions. You can pick up some shirts if you want from our event. So if you have any questions, probably mainly for the exploitation, just ask. But any others, just ask. I will be happy to answer.
Hi. Sorry. Hi, I have a question. Can you share some knowledge how or what tools do you use when you're writing a kernel exploit? Because once you trigger the panic, obviously, then there's a problem. But there's a lot of, well, small steps that you need to, when you're working on your exploit. Do you have any, can you share some, of your experience? What's the best approach and how to achieve it? It's much easier in user space, but when you're in kernel, obviously, kernel panic and you need to start all over.
Yeah. For example, best tool for researching kernel in Windows is WinDBG. Yeah.
I was thinking about Linux
Yeah.
and Android.
And for this one, we also introduce a CC shell cloning framework, when you can basically, after you get some exploits, you want maybe to do some kernel mode driver, and it's easier to, in this framework, based on C++, you can basically write the kernel mode driver inside, and you have just framework how to jump from user mode to kernel with this framework. That's the one thing. And second thing is that the kernel mode exploitation is not so hard, basically. When you got some, it just be distance about the knowledge. But when you're trying to go inside the kernel and how this kernel works, it's as easy as user mode, sometimes even easier. So my advice, for example, is try to, when you have some panic, try to reproduce and try to debug how it looks like, and then some static analysis. And then just start with playing with, for example, some CSS shell coding framework, introducing some code inside and experimenting. And you can, so basically debugger and this kind of framework can be your best friend.
Okay, thank you. More questions?
Okay, thank you very much. And